Good evening, everyone. It is currently 12:25 a.m. on the morning after the chemistry HSC. We're going to be going through the paper from start to finish just to give you guys some solutions and some explanations behind them all. But before I do, just introducing who I am. My name is Jeff. I run Catalyst Chemistry, and we're a fully online HSC chemistry program, which basically is there to help you get the dream marks you want in less time and in much less effort. So if that sounds interesting to you, I'll put the link to our website in the description, and you can check us out if you want to give us a try in the next term. Our next cohort starts for term one in uh, January, which is for module 6 for the year 12s and then module 1 starting for the year 11s. Link in the description. Maybe I'll put a pop-up on the screen somewhere as well, but that's basically what we do. I'll get into the paper straight away, and just to kind of give an overview of what I thought of the paper, it felt like a medium to hard difficulty paper, so actually not too bad. I'd say it was easier than 2020, 2021, 2022. I'd say it was harder than 2019 and 23, so probably a middle difficulty paper. And the difficult questions really only come in towards the end. Multiple choice had two difficult questions, but everything else was relatively standard and simple to solve. So we'll get straight through multiple choice. So question one, which two substances are members of the same homologous series? Of the options, when you're looking for a homologous series means the molecules differ by only CH2s being added on the chain, and the position of any functional groups or substituents are exactly the same. So looking at the options, A does make good sense because there is a hydroxyl on the first carbon in both of them, and they differ by the addition of this CH2 in the middle. B doesn't make sense because you have a hydroxyl, they're different functional groups. C doesn't make sense because whilst they both have a bromine on a carbon, there's also a hydroxyl that's been added on, so it doesn't make sense. And lastly, D, you have, again, difference in two. Uh, you have a difference because whilst the chlorine is on carbon one here, in both cases, you once again have an alkane as opposed to an alkene. So D doesn't make sense. A is the answer for one. Question two, Aboriginal and Torres Strait Islander peoples have been using leaching and flowing water over several days to prepare various foods from plants that can be toxic to humans. What was the reason for this? So essentially the reason why is to dissolve low solubility toxins, removing the cycasin from the cycad fruit, which means that you are able to remove the toxin and eat this food safely. Question three, which of the following compounds can be correctly described as an Arrhenius base when dissolved in water? Arrhenius base is a base that contains hydroxide within it, so OH minus, and will dissociate to make that OH minus when placed in water. Sodium nitrate does not have OH minus, sodium sulfate does not have OH minus, sodium chloride does not have OH minus, leaving just sodium hydroxide, which of course is NaOH, dissociating into Na plus AQ and OH minus, which fulfills the Arrhenius base general equation. Question four, infrared spectra of an organic compound is shown. You've got a deep, broad trough around 3,350. This is your OH from an alcohol. You've got a CH, you've got some miscellaneous signals at the bottom. This one could be potentially a CO. We don't really know, but we just say it could possibly be that. Of the options, the only one that therefore makes sense is the alcohol. Carboxylic acid, you would expect to see something more like a hairy beard, around just under 3,000. So it can't be B. For the aldehyde, for the ketone, which is C, you would expect to see instead something around 1,700, which we don't have here. And lastly, for D, that is just a hydrocarbon, which would not have this alcohol broad trough. So we can rule out D as well, leaving just A. Question five, which would be the best reagent to determine whether an unknown substance was 2-methylpropan-1-ol or 2-methylpropan-2-ol? So excuse the skeletal formula just to save time and multiple choice. You would do a 2-methylpropan-2-ol as such, and a 2-methylpropan-1-ol as such. Yeah. So the 2-methylpropan-1-ol, which is the one on the right here, this is a primary alcohol where you only have one carbon attached to the carbon that is attached to the hydroxyl. So this is a primary alcohol. The other alcohol is a tertiary alcohol because you have 1, 2, 3 carbons attached to the carbon attached to the hydroxyl. This is tertiary. Bromine water, now look at the options, is a test to differentiate saturated from unsaturated compounds. So you're looking for double bonds or triple bonds. We don't have any here in either molecule, so it wouldn't be a good test. Potassium nitrate is not useful here. C, sodium carbonate, would be used to identify a carboxylic acid, but again, we don't have a carboxylic acid here, so it's not a useful test. And acidified potassium permanganate, this is the best option because we are separating a primary from a tertiary alcohol. A primary alcohol will oxidize and change the color of the solution, whereas a tertiary will not. So D is the best option. Question 6. What is the hydroxide concentration of a solution of potassium hydroxide with a pH of 11? So as we know, pH plus pOH is equal to 14. pOH is therefore equal to 3 in this case, if you do 14 minus 11. And that correlates with a hydroxide concentration of 10 to the negative 3. And that correlates with option B. 7. Question 7, the following equilibrium was established in a container. We have 2 SO2 gas going to O2 gas, which is an equilibrium of 2 SO3 gas, and we have a delta H, which is negative 198 kilojoules per mole. Which of the following would increase the yield of SO3 gas? So option A, increasing the volume. This would shift towards the side with more moles, which is to the left, and that would actually decrease yield. Increasing the temperature would favor the endothermic direction, which in this case is the reverse, and that would also shift to the left and decrease your yield. Removing the product as it is formed. So if you were to remove SO3 and collect it somewhere, this would shift equilibrium right, replenishing the SO3 and effectively increasing the yield of SO3. So I think this should be C. And if you kept the temperature and volume constant, well, nothing's going to happen. So D doesn't make sense. Question 8. Which pair of ions produce different colors in a flame test? You have bromide, chloride. They do not form any color in flame test because they're both anions. Silver and hydroxide. Silver does not form a color in a flame, and nor does hydroxide, so you wouldn't see any colors here. Copper and calcium. Yes, you will see a difference because copper is going to form, of course, its signature blue-green flame, whilst calcium forms a brick red flame. And so C is the best option, and D, acetate and H2PO4 minus. This doesn't make sense. Both anions or anionic polyatomic ions, they're not going to show up colors. So question 9. Which of the following is the mass spectrum of ethanamine? Ethanamine we know is CCNH H. It has a molar mass of 24, or I'll write it out full, 2 times 12 2 times 12 simplified for multiple choice plus 14 plus 7. And if you sum this all up, this gives you 24, 38 plus 7 is 45 as your molecular ions mass per charge. So looking at the spectra, you're looking at the one that has a molecular ion at 45. And the one that sticks out immediately is B, where you have a signal at 45. And you can check the base peak against ethanamine to make sure it makes sense. So if you're looking at the base peak, the most abundant one, you're looking at a fragment of the molecule that has a molar mass of 30. And if you actually cut the molecule here, I believe, this gives you 14 for the CH2, and for the NH2, this gives you 16, which combined is a 30 mass per charge, and that would be your base peak. So B is the best option for 9. Question 10, the following system is at equilibrium. Propane-2 gas is in equilibrium with propane-2 gas and hydrogen gas. A catalyst added to the system, which row correctly identifies the change in the yield of propane-2 and the reaction rates. So if you add a catalyst, yield does not change. That's the most important thing to remember about that relationship at equilibrium. And the second thing is then that the rates of reverse and forward reaction will both decrease, because as we know, if you have an activation energy profile or an energy profile, and you were to lower the activation energy, you've now lowered the activation energy in both the forward and the reverse direction. So both forward and reverse rates will effectively increase because of a higher success rate of collisions. You'd expect yield to remain the same. You would expect both forward and reverse rates to increase equally. and therefore the option is B. Okay, 11 could be a little bit, yeah. So question 11 could be a little bit tricky. There's a few places you can make mistakes, but the answer is basically lead iodide. You need to write an icebox to make Pb2 plus and I2, or not I2, I minus 2I minus ICE. And you would be able to say that your iodide concentration initially is 0.1, since you have that NaI, sodium iodide, dissolving 100% in solution to make 0.1 moles per liter of iodide ions. Your starting concentration of lead is 0, since there's no common ion of that, and the change is going to be x plus 2x, and therefore x and 0.1 plus 2x. When you go to solve this question, they're asking you to find the solubility of lead iodide, which is X, the concentration of lead that dissolves it, since it's a 1-to-1 ratio. So the KSP of lead iodide is 9.8 times 10 to the negative 9 from your data sheet, which is equal to 0.1 plus 2x squared times by x. But you can apply small change assumption to simplify this expression by getting rid of 2x. 0.1 squared times x is equal to that number. And if you rearrange in terms of x, x is equal to 9.8 times 10 to the negative 9 divided by 0.1 squared. And so this gives you the answer as D. All right. Question 12. The structure of an organic base or organic substance is shown rather. What is the preferred IUPAC name for this substance? So you can see that you have a chlorine, you have an amide here, and you've got a ethyl coming off the amide telling you that this is in fact a secondary amide. So whenever you have an amide, the carbon that is attached to the carbonyl is the lowest priority, since amide will always take the highest priority in pretty much every situation. Your carbons are therefore numbered 1, 2, 3, and 4. And so the chloro is on carbon 3. You can already rule out options A and B. And you know that this is a butanamide. There are 4 carbons on this amide, so you can rule out D. And just to fact check ourselves, this ethyl on the end comes off the nitrogen, which means it needs a locant of N. N-ethyl butanamide, and you have 3 chloro, signifying the chlorine coming off of the 3rd carbon on the butanamide chain. So C is the best option for 12. Okay, question 13. A fuel has these enthalpies of combustion, negative 2057.8 kilojoules per mole and negative 48.9 kilojoules per gram. Which of the following correctly identifies the fuel? Okay, so you've been given enthalpies of combustion in terms of moles and grams. So you're essentially trying to find what the molar mass is. You want to find the measure of grams per mole. So the clever thing you can do here is you can do negative 2057.8 kilojoules per mole. Or I'll put it in terms of indices so it's a bit clearer. Kilojoules per mole divided by negative 48.9 kilojoules per gram. And once again, I'll put in indices per gram. Because when you put units into a division or multiplication, you treat them the same as essentially pro numerals. So this is going to give you, as a number, 46. Actually, let me just do it in my calculator. 2057.8 divided by 48.9 gives you, sorry, not 46, 42.08. And because the units, kilojoules cancel out, and the grams, you're dividing by grams to the negative 1, it is now grams per mole. And this gives you, in fact, the molar mass of propene, which is 42.1. All right. Question 14. Glycine, an amino acid, can react with itself or other amino acid monomers to form silk, a natural polymer. Glycine has a structure as follows. A section of silk is shown below. Which monomer could react with glycine to form this section of silk polymer? So immediately you know this is a condensation polymer because you have amine and carboxylic acid on alternating ends of this monomer. Now, you have to look at your polymer that you're given and at first identify where does this part appear first. And you can see that it makes up this section here. It makes up this section here. And then the pieces in between are slightly different. You can see that they have this methyl group coming off them, methyl group. But they do appear to have the same function groups on either end as well. So we're looking for a monomer that has a methyl group coming off of the carbon that is attached to the nitrogen. So we're looking for, on the carbon attached to nitrogen, there should be a methyl group. There isn't one on this molecule, so A is ruled out. B, you can see that there is a methyl group coming off of the carbon attached to the nitrogen, which tells us the monomer that's correct is B. And on the other end, we can verify that there is in fact a second carbon with a carbonyl and the hydroxyl, which makes that carboxylic acid that can form the amide linkage to the next monomer. Just to verify, C doesn't make sense because this is a double bond and there's no carboxylic acid. This is not how a condensation polymer works. And for D, it's not quite correct because we actually have a hydroxyl on that branch that comes off of the carbon. So that's not quite correct. Correct option is B. '15, the thermal decomposition of lithium peroxide is given by the equation shown. We have lithium peroxide solid in equilibrium with lithium oxide solid and oxygen gas. Mixture of lithium peroxide, lithium oxide, and oxygen were allowed to reach equilibrium two identical closed containers, P and Q, at the same temperature. The amount of lithium peroxide solid in container P is double that in container Q. The amount of lithium oxide in the same container, the amount of lithium oxide is the same in each container. What is the ratio of oxygen concentration in the container P to concentration of oxygen in container Q? Okay, so this is a really, really trick question where they tell you that the solid is double in one of the containers for lithium peroxide, and it makes you think that one of the containers is going to potentially have more oxygen forming. But in truth, your equilibrium expression for both of these cases is literally just the oxygen concentration since you exclude pure solids. So no matter how you change the concentration of lithium peroxide or lithium oxide, the amount of oxygen present at equilibrium, assuming you have enough solid to make the oxygen, the concentration will just remain unchanged. And so the ratio should therefore be 1:1. Question 16, which of the following is the overall reaction that takes place when a strong acid is added to a buffer containing equal amounts of acetic acid and acetate ions? Cool. So you're essentially looking for the equation that has, first of all, acetic acid and acetate, so you can rule out A. And you're looking for the case where you are adding in strong acid, which is where you are adding H3O plus. So you can rule out option B, because that's adding in OH minus. Now, the final two options, option D makes no sense because you're making a molecule that doesn't really, it's not really the way acetic acid works. It cannot take on another hydrogen just like that. So D doesn't make sense. We know that acetate can act as a base and it can accept a proton from H0 plus, which allows it to form acetic acid and for hydronium to form H2O. And so C is the best option for 16. Okay, so 17, there's an easy way if you know a hack, and otherwise there's a longer way that you have to prove mathematically. The easy way is if you had done a depth study during the year which looked at the relationship between pH and pKa in the lens of the Henderson-Hasselbalch equation, you would have known that at half equivalence, pH is actually equal to pKa. So that would mean that because the equivalence is at 20, at half equivalence, you know that pH equals pKa for the acid, and therefore you would be able to read off the pKa from the graph. pKa being equal to, therefore, about 1.91, which tells you it's going to be C. So we showed that pKa equals 1.91 for the first dissociation, and for the second dissociation, the half equivalence point lies at 30 mils. And because pH equals pK here again, that's about 6.30, and we know that the pK for the second dissociation is 6.3, and it will give you the answer C. But if you wanted the more mathematical proof, the way you think about this is that Ka is equal to the concentration of Ha times by A minus, sorry, not HA, H plus times A minus on concentration of HA. And at half equivalence point, you have a concentration of H plus, a concentration of A minus, which is exactly equal to your concentration of HA. Exactly equal, because you've added just enough base to neutralize half of your HA, and just enough base to therefore have that same amount of A minus present. That means that at half equivalence, your expression simplifies to Ka is equal to H plus, since the A minus and HA would cancel at this half equivalence point. And if you applied the negative log to both sides, you would then end up with the pKa and the negative log of H plus concentration, which, as we know, is of course pH. And this is the relationship that you could have proven to also figure out this question, which is actually in truth quite a nasty question if you didn't really know this relationship, but the answer here would be C. Question 18. A reaction mixture not at equilibrium is composed of both N2O4 gas and NO2 gas in a closed container. The reaction quotient in the system Q is given, and Q equals concentration of NO2 squared on N2O4 concentration. The rate of forward reaction is initially greater than the rate of reverse reaction, which diagram shows Q changes over time for this mixture. Okay, so it's important to note that you have a mixture already present, so you're not starting at a concentration of 0 as shown in A, and we can rule A out very quickly. Then we look at the Q expression, and we can see that it is representing the equation N2O4 that is in equilibrium with NO2 gas as follows. Okay, and then they tell us that the forward rate is greater than the reverse rate, which means that the reaction is going to proceed to the right. If the reaction is proceeding to the right, you're making more nitrogen dioxide, which means that the concentration of NO2 goes up and of N2O4 goes down, which has the net effect of increasing Q. So we're looking for a graph where Q is increasing, and the only two that satisfy that is A and B. But we already ruled out A because we have a mixture present of non-zero concentrations. So ruling out C and D, this leaves us with B, where we start at a non-zero concentration because we have a mixture of NO2 and N2O4 present, meaning our Q is non-zero. And because we have an increasing Q value over time, that correlates with the shift to the right. So B makes the most sense for 18. Okay, question 19. Which of the following compounds produces two doublets in the proton NMR spectrum? We have a few options. Let's talk through each of them. For option A, these hydrogens here are going to show a doublet because they only have one hydrogen on the neighboring carbon. This hydrogen is going to show a quartet. This hydrogen is going to show a septet because there are 6, and these two hydrogens are actually going to show a doublet because there's only one hydrogen on that neighboring carbon. So in fact, the answer is A. We'll go through the other three anyway. For B, these three are going to show a quartet. This is going to show a quintet. This is going to show a just a singlet. These are all identical, and they're all going to show a doublet. For C, and so you can rule out B, you only have one doublet. For C, you would see a singlet, you would see a septet, and you would see a doublet. Once again, only one doublet, and I'll just circle these on A to make it clear you have two. And for D, these two would show that doublet. This one would show a lot. This would show 9. I'm not even sure what that's called, so I'll just write 9. H here and here are identical. These would both show quintets. Sorry, not quintets. They would show quartets. Because they have 1, 2, 3 neighboring. These two would show hextet because it is 2 plus 3. And finally, this would show a triplet. And we only see one doublet in option D. I think that makes sense to me. So option A is the one that makes the most sense ultimately, as there are two doublets. Okay, question 20. The concentration of ascorbic acid in solution A was determined by titration. 25 ml sample of solution A was titrated with potassium hydroxide solution. 50 milligrams of ascorbic acid was added to a second 25 ml sample of solution A, which is titrated in the same way. Titration volumes for both titrations are given. Solution of 25 mils took 17.5 mils, and 25 mils plus 50 milligrams of ascorbic acid is 33.10 mils. So they ask you, what is the concentration of ascorbic acid in solution A? I'd probably start by turning the 50 milligrams into moles. So this is 0.05 grams, and turning that into moles of just, I'll say, acid, just to keep things simple. 0.050 divided by 176.124. Putting this in terms of moles, 0.05 divided by 176.124. This gives us 0.00028389089. I'll keep it simpler. 0.0283 for multiple choice in moles. So that means that the volume of titrant required to neutralize this was the difference between those two numbers. So 33.10 minus 17.5, 15.6 liters, milliliters of the titrant was required. It would be equal to 17.50 divided by 15.6 times by 0.000283 moles. 15.6 times by 0.000283, which gives 0.000317 moles. And therefore the concentration of acid is equal to 0.000317 divided by volume 0.025, which gives 1.27 thereabouts, times 10 to the negative 2. And that gives me D as my answer. All right, back from a break. It is now 1:03 a.m. and we will continue on through the short answer section. So we have 21 to 39, a very, very long paper. As I was mentioning before, I think on the whole, this short answer section was very, very much standard, very predictable for the most part, apart from question 35 and 39. So we'll walk through, we'll have a look through each of the solutions and um, yeah, that's pretty much it. As I was saying before, just to reintroduce who we are, Catalyst Chemistry, my name's Jeff, and we essentially run a online HSC chemistry program, which takes students from being average or not so good, or even a little bit above average, to reaching a complete full potential. And our program does that by taking you 3 weeks ahead of your class pace. So you learn faster than your classmates. You'll be constantly ahead of the class and you'll walk in the classroom knowing exactly what's going on each week. We find that 3 week runway is enough to just give you the perfect amount of time to do practice questions, trial papers, and it gives you a head start enough so that you've seen 3 weeks worth of questions more than your classmates, and that's actually what lifts you an extra 10%, 20% up above your classmates. It's that prevention of silly mistakes, the exposure to some harder questions before your exam, and that's what really makes a difference. So if you're interested in that, we have a link in the description to our website. You can click there and submit a form to join our waitlist because we are full until the new year. And if you have any questions, feel free to send us a comment or email to our email as well. So we'll see you there if you're keen, but otherwise we'll continue on with the speed run. So on to the short answers. Question 21, a solution of acetic acid reacts with magnesium metal. They say acetic acid reacts with magnesium. So writing the names of the products, we know this is going to be magnesium acetate, and you'll be making hydrogen gas because a metal and acid makes a salt. Because a metal and acid makes salt and hydrogen gas. So 2 marks there. The vinyl fluoride has been polymerized. In the box provided, draw a structural formula for a 6-carbon section of the polymer formed from the polymerization of vinyl fluoride. So this is going to be making a addition polymer. You're going to be attaching essentially carbons one after the other. So this would be your first monomer, sorry, F being attached onto the next monomer, which is exactly the same. And I would do exactly what they've given in that monomer. Just keep the fluorine in the same place, or the fluoride in the same place rather. And these are your 3 units. Now, I would put brackets around the sides and an N to signify that this polymer continues. I think this is probably the best, but I think there'd be flexibility if you, for example, put H's here. If they just wanted a 6-carbon section of the polymer, then maybe as well they might just want you to leave off the hydrogens as well. Hard to say entirely, but for me, I would put brackets like this and an N to show that this continues on. Question 23. Consider the following equilibrium system. You have your cobalt chloride solution, which is your case study from the syllabus. You see that the cobalt hydrate is pink and cobalt Cl4 2- is blue. When a solution of these ions and chloride ions is heated, the mixture becomes more blue. Relate the observed color change to the change in KEQ. So they're saying it's becoming more blue. That means as you heat, you are shifting right with the application of heat, increase in temperature. This implies the reaction is in fact endothermic. Delta H is greater than 0. As you're increasing temperature, shifting right means the forward direction is endothermic. So if you're going to relate this to KEQ, if you're shifting to the right, that would mean shifting to the right. Well, we'll explain it in words. So we'll say that an increase in temperature causes a shift to the right as the solution becomes more blue. So we know that it's a shift to the right. Shift to the right. Therefore, concentration of CO Cl4 2 minus and or CO Cl4 2 minus increases whilst concentration of CO H2O6 2 plus and concentration of Cl minus decrease. Therefore, Q equals concentration of CO Cl4 2 minus divided by, hang on, sorry, yep, that's right, CO H2O6 2 plus and Cl minus to the power of 4. Q has increased as the K value must have increased from a temperature increase. So I'd say something along the lines of that, where you're essentially relating that increase in temperature causes a shift to the right, concentration of COCl4 went up, and COH2O6 and Cl minus go down. Therefore, it means that your Q had to have increased. And as we know, temperature change only affects K. And once the K has changed to a higher value, your Q will slowly move back to your K, which means your Q increases. And as we see here, your Q is increasing, which signifies your K has to have increased. That's only possible in endothermic reaction if you have increased temperature. So that all ties together nicely. And maybe you can just say at the end that from a temperature increase in an endothermic forward reaction. Cool. Question 23. Question 24. Plot the boiling points for each series of compounds against the number of carbon atoms per molecule. So you've got boiling points and boiling points going up to 118. You have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14 lines. So we're just going to go up in units of 10, 0, 10, 20, 30, 40, 50, 60, 70, 80, 90, 100, 110, 120, 130. Adding a title just in case. Boiling points, I'll just say number of carbon atoms versus boiling point. And we can now plot for, firstly, let's do methanamine. Oh, sorry, there's -6. Okay. You can't do this in the HSC, but I can. I can cross off the 130. Let's move everything up. So we've got -10. The lowest value for methanamine is -6. So let's do these in crosses. For ethanamine is 17 here. Propan 1-amine 48. And butan 1-amine 78. Cool. Then we have the alcohols, which are 65. Do this in dots. 65. Ethanol 78. Propanol 97. Butanol 118. Now let's put a key. Alcohol cross equals amine. And then I would include, looks to me like a linear relationship. So I'll include a, oh, no, it's not a linear relationship. I think it's pretty linear for the most part. I'll include these lines. Okay. Part B, with reference to hydrogen bonding and dispersion forces, explain the trends in the boiling point data of these compounds within each series and between the series. Okay, so you're explaining basically that for methanamine and alcohol, these both have hydrogen bonding, but one of them has hydrogen bonding that is in fact stronger than the other, which explains why alcohol is at a higher boiling point for each carbon than amine. Okay, so as I always suggest, best responses will actually start with the lower boiling point substance and go up. This is of course not essential, but I think it's a time-saving tool. So I'll start by saying amines form H bonding, dipole dipole, and dispersion force. Dipole dipole and dispersion force. As the chain length increases, dispersion force increases due to a larger number of electrons, which increases the proportion or increases the ability to form temporary dipoles. And linking back to the graph, this explains the increasing linear trend on the graph. Then you'd move on to the alcohols. You've sort of explained the amines in terms of the intermolecular forces and then their trend. You'd then want to go in and say alcohols form H bonding, and I would say them explicitly via marker. H bonding, dipole, dipole, and dispersion force as well. However, the increased polarity of OH compared to NH leads to stronger H bonds forming, and you can put in brackets both molecules form one H bond per molecule. So that explains why hydroxyl is a higher boiling point compared to amine. H bonds forming. Therefore, alcohols of same chain length have higher BP. And you could note as well that these molecules of similar chain length would have quite similar dispersion force because their molar masses are pretty similar. Then you would say, as alcohol chain length increases, the dispersion force similarly increases similarly. However, the gradient of increase is less as the effect of the polar portion is being decreased proportionally more by the increasingly non-polar portion predominance. Something along those lines. Essentially, you have 4 marks here to pick up in my head. You have 2 marks for explaining the boiling point trends within each series. So, sorry. For explaining why the boiling points increase within each series. So 1 mark each. And then 1 mark, I would say, goes to comparing between the series and justifying why amines are lower than alcohol. So talking about amine intermolecular force and alcohol intermolecular force. In hindsight, probably actually could have been easier just to structure this as those 2 parts, but I've written it all out. It's all full here, so you can structure it differently, but I think they're the 4 marks. Okay, question 25. The concentration of phosphate ions in washing machine wastewater can be determined using colorimetry. A sample of washing machine wastewater was collected and diluted by quantitatively transferring 1 ml of the solution to a volumetric flask and making up the volume to 1 liter with distilled water. Standard phosphate solutions were prepared and analyzed with a colorimeter using an accepted method. The standard calibration curve is shown. Okay, let's just note straight away that there is a 1000 times dilution. The diluted sample was then analyzed using the same method as the standard solutions. The absorbance of the solution found to be 0.64. Determine the concentration of phosphate ions in a sample of the washing machine wastewater. Okay, so we have 0.64. Let's read that off the graph, drawing a dotted line across. We find the measure here correlates exactly to this line. We have 0 margin for error on a read like this, so it has to be, this is 0.7, so this is 0.78 milligrams per liter. So the concentration of phosphate in this is the diluted one, so say diluted, is 0.78 milligrams per liter. They want you to therefore find the concentration of phosphate ions in a sample of washing machine wastewater, which is 1000 times more, just checking, 1000 times more concentrated. So therefore, the concentration of PO4 minus in the initial washing machine water is 0.78 times by 1000, which is equal to, is it really milligrams per liter? It really is. Okay, so it'd be 780 milligrams per liter, which is the same as 0.78 grams per liter. They want it in moles per liter. So then you divide by the molar mass of phosphate, so 0.78 grams per liter divided by phosphate, which is periodic table. 30.97 plus 4 lots of 16, 0.78 divided by 0.78 divided by 30.97 plus 64 gives you 0.008213 moles per liter. And to be clear, this bottom section is in grams per mole, which is why it cancels these units. And just making sure. Yep. So checking out sig figs 0082 moles per liter to two significant figures should be your final answer on 25. Okay, cool. So you have, for question 26, you've been asked for, well, you've been given the equilibrium equation for the reaction of iodine with hydrogen cyanide in aqueous solution. I2 plus HCN goes to ICN plus I minus plus H plus. Time 0, I2 is added into a mixture of HCN, I minus, and H plus, bringing I2 to 2 times 10 to the negative 5. After 3 minutes, system was at equilibrium, and analysis of the mixture found that half of the I2 had reacted. Okay, so basically you're saying that you have 2 times 10 to the negative 5 at time 0. If you were to sketch this on an axis, you're saying after 3 minutes, half of the I2 reacted. So here, and you're at equilibrium by that point. So effectively you have this. And want you to stop at t equals 6. Okay. So I think this is the graph for part A. I presume 1 mark for plotting 2 correctly, 1 mark for plotting time at 3. Okay, using collision theory, explain the rate of reaction between time equals 0 and 6. Refer to I2 in your answer. Okay, so we know at time point 0, the reaction is proceeding in the forward direction faster than the reverse. And this is true until time point 3 when forward is equal to reverse. So we're going to explain those two situations. So you would say at time equals 0, forward reaction rate exceeds reverse as there are more successful collisions per second between reactants compared to products. And you could say this is due to concentration of I2 and concentration of HCN being above the equilibrium concentrations. From T equals, or T greater than 0 until T, or maybe I'll put it in terms of from T greater than 0 to less than 6, forward rate decreases as concentration of I2 decreases since frequency of collisions decreases. And then you can finally say, or you could also say reverse rate would be increasing as well. Increases as more products are formed. And then very finally, you could say at t equals 6. Oh, hang on, sorry. There should be t less than 3, sorry. And then you say from t is greater or equal than 3, forward rate equals reverse rate as I2 is now at equilibrium concentration. And I think they're the main things I will talk about. Just 3 parts. I'll talk about the starting rate, how rate changes, and how rate occurs at equilibria for 3 marks. Question 27. The following procedure is proposed to test for the presence of lead-2 and barium ions in water. Concentration 0.1 mole per liter. So you have 3 steps. Add excess 0.1 mole per liter sodium sulfate solution in precipitated form, then barium ions are present. Filter any precipitate produced, and add excess 0.1 mole per liter sodium bromide solution to filtrate. If precipitate is produced, then lead-2 ions are present. Explain why this procedure gives correct results when only barium ions are present, but not when both barium and lead-2 ions are present. Include one balanced chemical equation in your answer. Okay. Okay, so the big problem here is that if you were to try to precipitate a solution that contained both barium and lead with sulfate, as we know, sulfate precipitates with lead, mercury, silver, calcium, strontium, and barium. So it will precipitate with both barium and lead. So the first step uh, doesn't allow you to actually test if barium is present or not, because you would get a positive finding if you had lead. And then 3 would, for bromide, would allow you to test for lead on its own, since group 17 only precipitates the lead, mercury, and silver. So you'd be able to still identify lead, but you would not be able to identify barium if you had both of them in it. So we're essentially just writing that out in words. They ask you to include at least one chemical equation. Yeah. So if only barium ions are present, you'll get a positive finding for number 1, and then you'll get a negative finding for number 3, where you don't have any lead ions present. In contradiction, so that's the case where it would work, and you could write any of those equations. For example, we'll just write the simple one: barium 2 plus SO4 2 minus aqueous um, precipitates into barium sulfate solid. And then in the other case, this is the case where you have both barium and lead. What I'm saying is in part 1, if you add sulfate into a solution that contains both of these ions, the sulfate will actually precipitate both barium and lead sulfate at the same time. And you would have this equation again with the addition of Pb2 plus SO4 2 minus makes AQ going to be PbSO4 solid, which would mean you'd get a false positive for barium in the case where you have lead. However, for the third step, if you filter those precipitates away and you add sodium bromide, you would then have the reaction between lead 2 plus aqueous plus Br minus aqueous to go and make lead bromide solid. And this would be still a valid test to test for lead. But the problem is you can't separate the barium and lead, and you wouldn't be able to figure out if there's actually any barium in solution. So basically that in words. Question 27. Question 28. Iodic acid and sulfamic acid are monoprotic acids. 0.1 mole per liter of solution of iodic acid has a pH of 1.151, as does a 0.120 mole per liter solution of sulfamic acid. Show that neither iodic acid nor sulfamic acid dissociates completely in water, and determine which is the stronger acid. Okay, so two parts of this question. You have to firstly show that neither of these acids dissociates 100%. And you can show that either from going from pH to concentration or from the concentration to a pH. And let's do iodic acid first. So HI concentration is equal to 0.100. And for a pH of 1.51, the concentration of H plus from 1.151 is equal to the negative log of 1.151, which we already know is going to not be strong, but just to show it in the numbers, negative log of 1.151 is equal to, sorry, hang on, not negative log, apologies. It is 10 to the power of negative 1.151, which is equal to 0. 0.07063, which is of course less than 0.1, therefore not strong. And for the sulfamic acid, which has an even higher concentration, this is less than 0.12 concentration of sulfamic acid. For either. Because you show that the concentration of H plus is less than both of those concentrations. Okay, and then you want to show which is the stronger acid, and you would go to find the strength, you take the concentration of H plus, so strength is equal to concentration of H plus divided by the concentration of that acid. So for HI, this would be equal to 0.07063 divided by 0.1, which is 0.7063. If you multiply by 100%, then you now have 70.63 as your dissociation percentage. And for sulfamic acid, I'll just put it as sulfamic acid. This is 0.07063 divided by 0.12, which is equal to 0.07063 divided by 0.12 gives you instead 58.86% if you multiply by 100% as well. So you can see, based on the comparison of the percentages, the strength of HI is a stronger acid as it dissociates more. Cool. All right. Question 29. 150 mils of 0.2 mole per liter sodium hydroxide solution is added to 100 mils of 0.1 mole per liter sulfuric acid solution. Calculate the pH of the resulting solution, assuming that the volume of the resulting solution is 250 mils and that its temperature is 25 degrees Celsius. All right, cool. So you're essentially going to do a limiting reagent here, and then you're going to do no, you're not. You're just finding pH. Okay, cool. So starting with the moles of sodium hydroxide, NaOH, we can just turn it straight into OH because it's probably more relevant. The moles of OH minus is equal to 0.2 times by 0.15, N equals C times V, which is equal to 0.03. Just checking it anyway. 0.03 moles, and the moles of H plus from sulfuric acid is equal to 2 times 0.1 times 0.1, which is equal to 0.02 moles. So from that, we find out that the limiting reagent is in fact sulfuric acid. Limiting, and therefore excess moles of NaOH of NaOH minus is equal to 0.03 minus 0.02, which is equal to 0.01 moles excess. Therefore, the concentration of OH minus is equal to 0.01 divided by 0.25, which is equal to 0.04 moles per liter. And this is your concentration of hydroxide. To now find the POH, you can do the negative log of 0.04, since POH is the negative log of hydroxide concentration. Negative log of 0.04 gives you the answer of 1.39794, and to find pH, you do 14 minus 1.39794, which is going to give you 12.60 as your pH, and to 2 decimal places based on the question stem's 2 significant figures. Okay, question 29. Question 30, an equilibrium mixture of hydrogen, carbon dioxide, water, and carbon monoxide is in a closed 1 liter container at a fixed temperature as shown. H2 plus CO2 goes to H2O and CO with a KEQ of 1.6. The initial concentrations are H2 being equal to 1 mole per liter, CO2 0.5 mole per liter, H2O 0.4 mole per liter, and CO 2 moles per liter. An unknown amount of CO was added to the same container, and the temperature was kept constant. After the new equilibrium had been established, the concentration of H2O gas was found to be 0.2 mole per liter. Using this information, calculate the unknown amount in mole of CO that was added to the container. All right, so essentially you're just going to need to do an ice table and solve it. So we'll just do that. H2 plus CO2 goes to H2O plus CO. You have then ICE. Your initial concentrations are told to you as 1, 0.5, 0.4, and 2. H2O was found to be 0.2 after equilibrium established. There's no coefficients in your equation, so you don't need to account for any ratios. The change is therefore minus 0.2, minus 0.2, which gives you 1.8. And this is plus 0.2, plus 0.2, 1.2, 0.7. Just checking we haven't missed anything. 1 liter container. Sure. Okay. And we can just check these concentrations. I'll just put them into the 0.2 times 1.8 divided by 1.2 divided by 0.7. Does not give the KEQ. All right, I missed the CO that was added in. Okay, good thing we checked, because this concentration does not equal KEQ. So we know how much H2O changed by, and CO is going to decrease by 0.2, but before that it's going to increase by some amount. Let's say it's X. Plus X and then minus 0.2. So this is going to end up being 1.8 plus X. And so 1.8 plus X times by 0.2 divided by 1.2 times 0.7. KEQ is equal to that. And we know that this is equal to therefore 1.6. Solving, we can move everything across to the right. 1.6 divided by 0.2 times by 1.2 times by 0.7. 1.8 plus x is equal to 6.72. And if we test that again in our, as a concentration 1 liter as 4.92, and so the number of moles of CO added is equal to x times by 1 liter, which is equal to simply 4.92 moles. And our answer, as we have technically used this 1 liter to turn everything into moles, our answer should be actually left to one significant figure. So final answer is 5 moles. All right. Question 31. The atom economy of a reaction is a measure of the mass of atoms in the starting materials that are incorporated into the desired product. Higher activation energy means lower mass of waste products. Urea can be produced in a variety of ways. One way is to react ammonia, high toxicity, with phosgene, high toxicity. Another way is to react ammonia with dimethyl carbonate, which has low toxicity. The chemical equations and atom economy for these two processes are provided. Okay. Which of the two processes is preferable for urea production? Justify your answer with reference to the information provided. Okay. Cool. So there's two things you're taking into account in this response. You're writing about atom economy and you're writing about toxicity. So I'd split it into two separate parts. The first thing they introduce in the question stem is toxicity. So I'd probably talk about that first. So I'd have a subheading toxicity. And I would say that firstly, reaction with DMC is less toxic compared to reaction with phosgene, since phosgene is toxic, highly toxic, whilst DMC is less toxic. So toxicity first. I think that's pretty much enough. And then atom economy. Reaction with DMC has higher atom economy, 48.4%, and just quote numbers from the question, 48.4%, which leads to less byproduct compared to phosgene. Phosphogene's 35.9% atom economy. This lowers production cost and environmental waste. You could also mention in the toxicity that therefore this is environmental detrimental. If toxic method, more toxic method is used. And you have a conclusion at the end for the third mark. Therefore, DMC reaction is preferred for lower toxicity and increased atom economy. Okay. Question 32. Calculate the concentration of cadmium ions in a saturated solution of cadmium phosphate. You get given the KSP, and you essentially just need to work out the concentrations. So KSP of solutions given. First thing you're going to write is an equation. So CD3 PO4 2 dissociates into CD3 of these 2 plus 2 phosphate 3 minus. And if you're going to work into a KSP, this means that once X amount of cadmium dissociates, you're going to have plus 3x plus 2x 3x 2x minus x 0. So then you end up with a KSP expression, which is equal to cadmium 2 plus cubed times phosphate 3 minus squared. Subbing in your numbers, you end up with 3x cubed times by 2x squared. And you can equate this to the KSP 2.53 times 10 to the negative 33 is equal to 3 cubed is equal to 27 times by 4 is equal to 108 times x to the power of 5. Moving the 108 across, 2.53 times 10 to the negative 33 divided by 108. X to the power of 5 equals 2.34259 dot 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 times 10 to the negative 35. X equals 5, and answer is 1.1856 times 10 to the negative 7. And you can simplify this down to how many sig figs? We've got 3 in the question stem. That's all we've used. So this would be 1.19 times 10 to the negative 7 moles per liter is X. And if we're trying to find the concentration of cadmium ions, then CD2 plus is equal to 3 times X at equilibrium. So we would multiply this by 3. I would keep the exact number, sorry, so maybe not simplifying here. And this gives instead 3.5568 times 10 to the negative 7, simplifying to 3.56 times 10 to the negative 7 to 3 significant figures. And I think this is the answer. Okay. Making sure of units, mole per liter. Okay. Question 33. Identify the shape around the central carbon atom in each molecule from acetone being reduced. So they're talking about the central carbon atom here and here. So to be really clear, I'll just draw out the full thing just so we don't have any confusion at all. So this is acetone first, and then if you drew out propan-2-ol, the trick is that there is in fact a hydrogen on this carbon, and it is not the same geometry as acetone. So for acetone, the shape is going to be a trigonal planar due to 3 bonding groups and no lone pairs. And then for propan-2-ol, it's going to be tetrahedral because you have 4 bonding groups and no lone pairs. Cool. Part B, explain how 13 carbon NMR spec could be used to monitor the progress of this reaction. this was interestingly the question I predicted to come up in the exam in our predictions. So it did come, but not in as long of a response as I would have thought. So essentially, you would be looking at your carbon spectra, and for the two different molecules, the biggest difference you see is that for acetone, you would only have two carbon regions. You would have one and two. But for propan-2-ol, oh no, you'd have two either way. You'd have two carbon regions either way. However, they will have very different chemical shifts. So the carbonyl, as opposed to the hydroxyl, have different chemical shifts. Just to flick across to a data sheet, um, these would look like these. Just clear all this out. You would see in your carbonyl, you would see a aldehyde or ketone. In this case, it's a ketone. So you're going to see a signal from 190 to 220 ppm, which initially is very high. And as the reaction proceeds, this will decrease as you have less and less and less ketone. But what that will be replaced by is a alcohol 50 to 90 signal, which will, as the other signal decreases, the alcohol one increases between 50 to 90. And the other signals for the other carbon regions should pretty much just be either this one here for the aldehyde or this one here. So something in the range of 5 to 50 as the other signal, you would see those two kind of exchanging as well. But the main feature you'd want to watch out for is going to be the exchange of the signals for ketone versus alcohol. Okay. So basically putting that into words, you would say that just identifying acetone has two carbon regions and it has the 190 to 220 ppm signal for aldehyde, for ketone rather, for ketone C11O, and it has a, I think it was 20 to 50, just going back to check. Yep, 20 to 50, 20 to 50 ppm signal for CCO. And then the propan 2-ol, two carbon regions as well, but it has a 50 to 90 ppm signal for, let's just quote it exactly, it's this C to the single bond oxygen. Like so. And you have a 5 to 40 ppm signal for C to C. Therefore, as reaction proceeds, the acetones two signals decrease in intensity, whilst the propan 2-ols signals increase in intensity until the reaction reaches completion. Okay. So you'd monitor the progress based on how much has been converted from one to the other. And I think that's pretty much it. So yeah, you'll be looking at the proportion of those signals, how far they've gone down or how far they've increased. That tells you how far along the progress of the reaction is. Okay, Question 34. Again, in our predictions, we are pleased to say this was in them. So we predicted there'd be a conductometric titration this year. We thought it was due, and in fact, it did come. So question stem says an aqueous solution of ammonia is added to a solution containing hydrochloric acid. Plot of conductivity against volume of ammonia solutions added as shown. The temperature of the solution is kept constant throughout, and the conductivity of the solution is corrected for dilution. The relative conductivities of some relevant ions are shown in the table. So they've been very generous to even give you that. Explain the shape of the graph. Include two balanced chemical equations in your answer. Okay. Ammonia is being added. Hydrochloric acid is here. So I would discuss the point at 0 mils added from 0 to like, oh, it's curved. Let's say 4.5. It doesn't quite look like 4.5 to be honest. It looks more like 4.4. But yeah, curved paper, I actually can't tell. So we'll be discussing point 1, point 2, point 3, and point 4, going on from 4.4 mils onwards. So I'll just label on the graph. I think it's probably easier that way. I won't write the full response for this one. I'll say point 1, you have a very high conductivity because HCl has completely ionized into H plus and Cl minus. This leads to a very high concentration of H plus as well as Cl minus, but in particular H plus, which is the most mobile charge carrier of the four and leads to the highest conductivity at 0 mils of ammonia being added, justifying this as a strong acid. From point 1 to point 2, or from volume 0 to volume 4.4, ammonia is being added into the system. And so ammonia, NH3, is able to react, or you can either show it, yeah, we can just show it reacting with hydroxide. Sorry, not hydroxide, with H plus. NH3 plus H plus goes to form NH4 plus as a net ionic equation. And you can say that therefore, as ammonia is added, NH3 reacts with H plus, which forms NH4 plus and decreases the H plus concentration in solution. That leads to a decrease in conductivity because the concentration of H plus ions decreases, and so the conductivity they contribute also decreases over time. Point 3 is, of course, your equivalence point. At volume 4.4, or whatever it is actually on the paper, I can't really read it properly. 4.4 mils, you have your equivalence point where you have complete neutralization of H plus in solution, complete neutralization of H plus, which leads to your lowest point of conductivity, where all of the H plus has been removed, and you only have Cl minus remaining in solution, which is what's making this conductivity non-zero. It's important to note that too. And if you want to go above and beyond in section 2, I should go back. You should also say, as you're removing H plus from solution, you are creating a positive NH4 plus ion, which is actually contributing some ions into the solution and meaning your conductivity drop, instead of dropping all the way down for the decrease in H plus, it's actually not as big of a decrease as if it was just accounting for the decrease of H plus. You could also then say at point 3, because this is what reminded me, that you actually also have NH4 plus in solution at the same time. So you have two ions, making sure that your equivalence point conductivity is non-zero. Finally, from point 4, whereas pretty much 4.4 mils onwards, you are just adding weak base into solution, which is dissociating into OH minus, and you can show NH3 reacting with water, for example, as another equation. to make NH4 plus OH minus. Excuse writing into the no writing space. But essentially you have this equation and you say that only a small percentage of ammonia dissociates into NH4 plus and OH minus, which means that the conductivity only very slightly increases from 0.3 onwards. And that pretty much wraps up this response, as there's very clear 4-mark allocation where you have 1 mark for the starting point, 1 mark for the decrease, 1 mark for the equivalence point, 1 mark for the increase after equivalence. And that's pretty much it. And of course, having 2 equations, there's plenty to choose from here. It's now 2:16 a.m. We've taken a short break before question 35. We're getting through this paper, but before we move on again, just a quick reminder. I guess, again, just saying, my name is Jeff. I'm the founder of Catalyst Chemistry, and we work through HSC chemistry over the year, and we place you well ahead of your class cohort to make sure that you get the best marks possible internally, and then ultimately we place you ahead of the state to get you the best marks externally. So if getting a band 6 or a high band 5 or whatever your goal actually is, we can get you closer to there or even above it. If you are keen, the website is in the description. You can submit a form to sign up for our waitlist as we open a few new classes next year in 2025. We are currently full at capacity, so we cannot take any more students for the time being, but if that's interesting for you, send us a form and we'll reach back out in probably late November, early December to see if we have a place available for you. Cool. So let's move on to question 35. We have 3 carboxylic acids X, Y, and Z, and they're analyzed to determine their identities. Both Y and Z react rapidly with bromine water in the absence of UV light, but X does not. A 0.1 gram sample of Y reacts with the same amount of bromine as 0.2 gram sample of Z. Separate 0.1 gram samples of X, Y, Z are titrated with 0.0617 moles per liter of sodium hydroxide solution. The titer volumes are shown. Both Y and Z can undergo hydration reactions in the presence of a suitable catalyst. Two products possible for hydration of Y, but only one is possible for Z. Identify which structures 1, 2, and 3 in the table are X, Y, and Z. Justify your answer to the information provided. So the best way to do this, I'll just kind of scribble over the information and rule out and rule in things. So for Y and Z, they both react with bromine in the absence of UV light, which means they have some sort of unsaturated bond, whether it's a triple bond or a double bond. So looking at the structures, we see that structure 1 has a carbon-to-carbon double bond, structure 3 has a carbon-to-carbon double bond, but structure 2 does not. And that immediately tells us that structure 2 is in fact X. And that's enough information for us to pretty much get there, but we'll justify it in terms of everything else as well. A 0.1 gram sample of Y reacts with the same amount of bromine as a 0.2 gram sample of Z. Mm, oh, right. Okay. So yeah, because one has a double molar mass compared to the other, it will react with the same amount of bromine if you only have twice the amount of Z. So that tells you that structure 3 is Z and structure 1 is Y. Because Y will have half of the mass of the same amount or same number of moles compared to 3. Let me just fact check myself. 0.1 grams to 0.2 grams. Yep, that makes sense to me. Let's justify everything else. Y and Z can undergo hydration reaction in the presence of a suitable catalyst. 2 products are possible with the hydration of Y, but only 1 product is possible with Z. Yep, so that pretty much confirms what we've found. If you have 2 products possible for Y, that is because when you hydrate, you can either place the OH on the first carbon, or you can place the OH on the second carbon, and they are 2 possibilities when you hydrate. because there will be different unique molecules. But in the case of structure 3, the molecule is symmetrical, and this double bond is right in the middle. So regardless of whether you place the OH here or you place the OH here, the molecule is going to be exactly the same. It'll be on the third carbon. You read it the same either way. So that confirms once again, this is Z and Y is the structure 1. Oh, okay. So then coming back to the middle section, you're essentially just calculating for each of these, the moles that you have. So you would have, in each case, 0.1 grams divided by the molar mass. So the moles of Y would be equal to 1 on 72.062, which is equal to 1 on 72 on 72.062 is equal to 0.013876. So if you had, and the moles of, I'll just do each of them first. Moles of X would be equal to 1 on 74.078 equals 74.078 is equal to 0.013499. And moles of Z is equal to 1 on 144.124, which is 0.006938. Mole, mole, mole. So then you can also calculate the moles of hydroxide using each of these titrations. So then the moles for X from here is 0.02188 times by the concentration 0.0617. 0.02188 times 0.0617 gives you 0.00134999 moles, which links up correctly with X. You do the same for Y and Z. For Y, it would be 0.02249 times 0.0617, which is exactly the same as Z, by the way. So I'll just put these to arrows, 0.02249 times by 0.0617 is equal to 0.0013876 moles of hydroxide. And that makes sense that Y and Z are the two that require the same amount of moles, and Z would require 2 times the moles since it is diprotic, as it has 2 carboxylic acid groups, and then for Y, it has the single proton and it matches this mole amount exactly. So we've verified once again that Z is the same as the Z volume matches with the Z, the Y volume matches with structure 1, and then the X volume matches with structure 2. And we've confirmed through each of the pieces of evidence, which is, to summarize, going back over it, the bromine water test, the amounts they react by, the titration amounts, and then lastly, the hydration information. So 4 pieces of information that you really have to discuss. That the identities are Y, X, and Z. So if you had discussed all 4 of those in good depth and you got the correct answers, I think you're in for a good mark on this one. One thing I would say that is probably valuable to include is the equations for the hydration between Y, Z, and the hydration of Y and Z. So it's probably worthwhile showing those equations, how you can actually form the 2 different molecules, but I won't show them on this walkthrough. Okay, question 36. 14.7 grams of solid sodium hydrogen carbonate was reacted with 120 mils of 1.5 mole per liter hydrochloric acid with a density of 1.02 grams per mil in a calorimeter. The temperature of the solution before and after the reaction was recorded, goes from 21.5 to 11.5. Assume that all CO2 produced is lost from the reaction solution and that the specific heat capacity of the reaction solution is 3.8 joules per Kelvin per gram. What is the enthalpy of reaction? Okay, so fair bit going on here. First thing that's required is to find out how many moles actually reacted. And I think this is a case of a limiting reagent. So the first thing we'll find is the moles of NaHCO3, which is equal to 14.7 grams divided by 84.008 grams mole. 14.7 divided by 84.008 gives you 0.17498 moles as your sodium bicarbonate. Then you have 120 mils of 1.5 mole per liter hydrochloric acid solution. So to find the moles of HCl, we don't need to take into account density. We just say it is concentration times volume, 120 or 0.120 times by 1.5 equals to 0.180. Therefore, our limiting reagent is our bicarbonate. And the moles reacted we'd take from this value. Just to know the ratio for sure, we can show an equation between NaHCO3 plus HCl. Always good practice to have an equation. Makes NaCl AQ plus H2O plus CO2. And this is in fact what our equation is going to read. So the limiting reagent makes sense as NaHCO3, and therefore the moles of water formed, because this is a neutralization, moles of water formed is equal to 0.17498 in a 1-to-1 ratio with NaHCO3. So then the difficult part of this question is actually in finding the mass. There's information that's provided towards the end that says, assume all CO2 produced is lost from the reaction solution and that the specific heat capacity is now this. They want you to process that you've added in a mass and that some of that mass has been lost in this final solution. So the mass of the solution is equal to the mass of the HCl excess solution. So it's the mass of the HCl solution plus the mass of NaHCO3 minus the mass of CO2 that you lose. And so all that comes to 120 mils times by 1.02 grams per mil plus 14.7 grams minus, for CO2 you lose 0.17498 multiplied by 12.01 plus 32. So processing that in the calculator, you end up getting 129.39 grams. And so to find your Q is equal to 129.3 grams, your mass, times by 3.80 joules per Kelvin per gram, which is your C, times by delta T, which is -10. Giving you minus 4913.4. You've had a heat loss. And finally, your delta H is going to be equal to negative Q on N, negative 4913.4 divided by your N, which is the moles of water, because it is a neutralization, 0.17498 0.17498. So this is in joules. This answer is now in joules per mole. And to change it into kilojoules per mole, we need to multiply by 1,000. So I'll put it in 28,079.8 joules per mole, which is equal to 28.1 kilojoules per mole, to three significant figures. Okay, and that's 36. So 37, the relationship between equilibrium constant KEQ and delta G for any reaction is shown on the graph for a limited range of delta G values. The delta H and T delta S values for the reaction between copper sulfide and oxygen are provided. Explain with reference to the information provided why this reaction proceeds to completion rather than coming to equilibrium. So it's your standard delta G question for 3 marks. I think the first step is obviously calculating delta G. So delta G is equal to delta H minus T delta S, which in this case is equal to minus 217 minus 3, which is equal to would be equal to minus 214 kilojoules per mole. That seems very far to the left. Does this make sense? Okay, so I think this is the right number, but if you have a very large delta G, it means your equilibrium constant is very, very, very large and positive. So the more negative your delta G becomes, the larger your equilibrium constant becomes. So that's what the data is basically saying. The data shows larger negative delta G correlates with larger positive KEQ, as delta G is very large and negative. The reaction here would have a very large and positive KEQ. Therefore, reaction is spontaneous in forward direction and likely proceeds to completion. I think that's pretty much it. You just reason why delta G is negative in terms of the maths. You can show the KEQ expression as well if you wanted to, and just say that KEQ is equal to concentration of SO2 on O2 concentration. And basically that you'd have lots and lots of SO2 and very little O2 once the reaction has reached equilibrium, which is consistent with a completion of the reaction. Okay. 38, you have compounds A, B that are isomers with C3H7X, where X is a halogen. The mass spectrum for compound A is shown. Compounds A and B undergo substitution reaction in the presence of hydroxide ions producing alcohol C and D. Compound D can be oxidized to a ketone. Compound C can also be oxidized but does not produce a ketone. Compound E can be produced by refluxing 3-methylbutanoic acid with one of the alcohols C or D in the presence of a catalyst. The proton NMR for compound E contains the following features. They go ask you draw the structure of compounds A, B, and E and explain with reference to the data. Okay, cool. So starting off, we know that C3H7X X is a halogen. We look at the mass spectrum for A and we're immediately looking if it's a halogen in particular mass spectrum, is it chlorine or bromine? And we can see that the two signals right up by 120, 122, 122 and 124, these appear to be in a 1-to-1 ratio, almost 51 to 49, when it's very slightly lower than the other. This is indicative of bromine. So we'd be thinking that compound A and B are C3H7Br. Compound A and B can be substituted in the presence of hydroxide ions to produce alcohol C and D, and compound D can be oxidized to a ketone. So we know that D has to be a secondary alcohol, while C, it can be oxidized and it does not produce a ketone, which means it is a primary alcohol. That tells us that A is in fact C, 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 H, 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 with a Br on one of the end terminal carbons as follows. So this is A, and B is going to be instead the version where you have Br on the second carbon like so. And this is B. You then know C is therefore, we don't have to draw it, but it's C is the bromine that's been substituted out with an OH, and for D, this is Br that has been substituted out for a OH as well. Finally, for E, that can be produced by refluxing 3-methylbutanoic acid with one of the alcohols C or D in the presence of a catalyst, and to figure out whether it is C or D that you've reacted with. So it tells you, I mean, two options that you really can have. Let's just draw them out. I want to keep the data in the screen. So C, 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 let's say this is the methylbutanoic acid. C, 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 O, H, 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 H. Sorry, there's a 3-methyl. So that would be 1, 2, 3 over here. And then on the other side, you have your propan 1-ol in this case. Okay, so this is one option. Or the other option is where you have instead C, H, 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 as so. Okay, so then now you need to show which of these will have a, well, 6 different hydrogen regions. And looking at it immediately, I'm leaning towards the top molecule because you have 1, 2, 3, 1, 2, 3. They are identical. 1, 1, 2, 3, 1, 2, 3. They are identical. This is unique. This is unique. This is unique. 1, 2, 3, 4, 5 regions only. Whereas the top one has this being unique, this being unique, this being unique, this is unique. We are out of colors almost. These 6 are unique. And then finally, this one down here is unique on its own. So based on the number of signals that you can possibly have, it already rules out the bottom one. You know that it has to be this molecule. And let's just correlate all of those signals to what they actually correlate to. So you would have a integration of, I'll use I as integration of 3. And for this, you would have a splitting of 3. So this is likely your chemical shift of 0.95. For this, you would have an integration of 2, and you'd have a splitting of 6 because you have 5 neighboring hydrogens. So this likely correlates to this. For these two, you have an integration of 2 and a splitting of 3. So this likely correlates to, it could well be this bottom one here, being in closer proximity to an oxygen, could explain why it's more shifted with a bit of deshielding. Then moving up to the other side, this would likely have a integration of 2 and a splitting of 2, which probably correlates with the 2.2. This H here is going to have 1, 2, 3, 4, 5, 6, 7, 8, 9 splits with an integration of 1. So this correlates with this. And finally, these 6 yellow hydrogens, they are going to have an integration of 6 and a splitting of 2. Double it. I think I've allocated 1 incorrect. Sorry. Going back to here, this one, these blue ones should instead be the multiplet with a 2 in it. And finally, these yellow regions off to the right are the doublet with 6. Doublet with 6 integration. And so you know your molecule is, if you were to name it, just for the sake of it, you know it is propyl 3-methyl butanoate. And that's your molecule there. Okay. Final question. All right, we've come a long way. As we walk into the final question of the evening, it is now 2:51 a.m. We have a little bit of time left in our exam if we were doing this in real time. So let's get through this one to finish us off. Water and octane 1-ol do not mix when an aqueous solution of bromoacetic acid BrCH2COH is shaken with octane 1-ol. An equilibrium system is established between bromoacetic acid dissolved in the octane 1-ol and in the water. BrCH2COOH aqueous is in equilibrium with BrCH2COOH in octanol. The equilibrium constant expression for this system is KEQ equals the bromoacetic acid dissolved in octanol divided by the bromoacetic acid dissolved in water. An aqueous solution of bromoacetic acid with initial concentration of 0.1 mole per liter is shaken with an equal volume of octane 1-ol. Bromoacetic acid does not dissociate in octane 1-ol, but does dissociate in water with Ka equals 1.29 times 10 to the negative 3. When the system has reached equilibrium, the H plus concentration is 9.18 times 10 to the negative 3 moles per liter. Calculate the equilibrium concentration of aqueous bromoacetic acid and hence, or otherwise, calculate the KEQ for the octane 1-ol and water system. So this question is difficult. There's no two ways about it. The way that I would approach it is I would first start by attacking the first part of the question, which asks you to calculate the equilibrium concentration of the aqueous bromoacetic acid. So you can do this because you have the concentration of H plus and a Ka. And when you're talking about the aqueous bromoacidic acid, you're talking about the bromoacidic acid that dissociates in water only. Because as they say in the stem, bromoacidic acid does not dissociate in octane 1-ol, but does dissociate in water with a Ka of this and a H plus concentration of this. So essentially, Ka, as we know, and I'll represent BrCH2COH as HA for simplicity of my working. Ka is equal to HA, nope, is equal to H plus times by A minus divided by HA. And this is standard for any acid dissociation. So in this case, we know that the H plus concentration is going to be equal to the A minus concentration, which is equal to 9.18 times 10 to the negative 3. Since they dissociate in a 1-to-1 ratio for bromoacidic acid, there's only one ionizable proton. Therefore, if you rearrange the Ka expression in terms of HA concentration, HA within the aqueous solution, you would be able to find that 9.18 squared, or times 10 to the negative 3, squared divided by Ka, which is given as 1.29 times 10 to the negative 3. This HA concentration is 9.18 times 10 to the negative 3. So we need to do this all squared divided by 1.29 times 10 to the negative 3. Equals 0.065327. I'm not even kidding. My calculator is like so faint. You cannot even see it. It's like it's the true symbolic end of this chemistry exam. We have that concentration there. So we have the concentration of HA aqueous ions, and you'd be able to then go on and find you'd then be able to go on and find the concentration of HA in the octanol, and the way that we go about that. So let's rule a line there. The way that I found this easiest to visualize, because truthfully I did this question as soon as possible after the exam because everyone said it was very difficult. The way that I like to imagine it is you imagine a beaker where you have two 1 liter components. You have 1 liter of octane 1-ol, and you have 1 liter of water. So essentially, what you're saying is that the moles of HA existing as HA or A minus in solution, or really truly H plus or A minus in solution, is equal to 0.065327 moles plus 9.18 times 10 to the negative 3 moles. Calculator is dead. I have to get a new one. Okay. So we have 0.065327. Let me get the exact number. The new calculator, 9.18. 9.18 times 10 to the negative 3 squared. 1.29 times 10 to the negative 3 gives this exact number. I'll store it as A. And A plus 9.18 times 10 to the negative 3 gives you 0.07450744 moles. Say this is B. Okay. So what this tells you is that of all the HA that initially existed in the that initially existed in the 0.1 mole per liter solution, 0.745 moles per liter of that amount is going to exist in aqueous solution. That means that the remainder of that difference between 0.1 and 0.0745 moles exists as aqueous HA, undissociated in octan 1-ol. So the moles of HA dissolved in octan 1-ol is equal to 0.1 moles minus 0.07450744 moles. 0.1 minus answer, and this is equal to 0.025492558 moles. Say this is C. So we have three numbers now, and we have all we need to actually find your ending concentration. Your concentration of BrCH2COH in octan 1-ol, this is what we found as C. The moles present in 1 liter is that amount. Hence, that is your concentration of BrCH2COOH in octan 1-ol. And our concentration of bromoacidic acid in aqueous solution as bromoacidic acid, not bromoacetate, to be clear. This is A, not B. And so we have all that we need. We have all that we need. We can now go and say KEQ is equal to the concentration of bromoacidic acid dissolved in octan 1-ol, which is C. And we can take bromoacidic acid dissolved in aqueous solution, which is A. And placing C on A divided by A, you get out the answer 0.390227, which is 0.390 for three significant figures. And with that, that brings us to the very, very end of the HSC Chemistry Exam 2024. It's been a pleasure of a year teaching many, many of you through our workshops, and of course teaching all the Catalyst students, from some of you for the last 2 years and some of you only for 1 term. But wherever you joined us along the way, we hope you found it extremely beneficial to be part of what we've tried to put you through, which is an accelerated program, which takes you 3 weeks ahead of class pace throughout the year. And we finish off with an exam program, exam intensive, which places you through 4 exams. Everything aside, next year, 2025, if you have any friends, family, or you are a student in the class of 25 or 26, we do have a wait list for 2025 for both our Year 11 and Year 12 streams. So if you're interested in joining, please send us a message on our contact us form in the description. I'll put a link up somewhere here maybe as well, but in the description there'll be a link. Click on that and you'll be redirected to our website where you can fill in a form and just tell us a bit about your situation. And we'll open our waitlist probably late November, December of 2024. So that's all from me. Thank you so much for listening to this point. If you've stayed along, genuinely, I don't know how you have. The final thing, if you are interested in potentially doing some work at Catalyst, whether that's some teaching work as a tutor, marking work, or actually looking into growing our program, send us a message too, because we are looking for a few talented individuals to join our team in 2025. So that's the final thing. And with that, I'll conclude. Thank you for listening. I'll see you next time. Bye.